maybe it's a good thing. Ready to do more volumes? Okay, more volumes. Oh no, but we're gonna have fun with that, I'm sure. Did you figure that one out? I mean, you have to start simple. Just do just a curve and just a line. See what you get. Because that one is messy to begin with. See how you get that one, then. Yeah, but it's all slanted, so you have to account for the, because your shape will be, as you guys doing yesterday, perpendicular to the tangent line, so you have to account for that. If we allow the change of, we'll talk about it after classes. I don't want to talk about it now. Okay, never mind. So more volumes of revolution. So far we're talking about the disk method. And so again, the formula that we came up with was pi integral from a to b f of x squared dx. And that's if you rotate around the x or around any horizontal axis. We'll deal with that a little later today. And if you rotate around the verticals, you have y's, dy's. So I want to do this example. Rotate the region bounded by the following functions: y equals square root of x equals 4, and rotate around the y-axis. We're actually going to derive a new formula after doing this problem. So if I sketch a graph of this thing, so here's the square root, and let's say this is a 4. So the region bounded, so what is that? That's region, right? So when you rotate, are you guys already doing it? Not waiting? Right, this is the thing we're kind of going to rotate. So whatever you call that shape. Can you picture that? This whole thing will kind of a, but it connects in the middle. It's kind of a, I don't know what you call it. What? Okay. Never mind. It's whatever the shape. So let's talk about this. How should we set this thing up? So one way to think about this, again, if we just use our basic geometric skills, I mean, we can go ahead and find the volume of just rotating x equals 4. So that's some kind of a cylinder, right? And then I can find the volume bounded by, under the square root function when I look this way. So this will actually be this kind of a funnel-looking thing, right? If I, what? No, we actually want to try to find whatever's left, right? Well, because this is the bounded region. So we're not doing the funnel, we're doing what's, hang on there. We're not there yet. But yeah, I mean, eventually we're going to move into that direction. But from with the tools that we have right now, okay. So if if I just rotate if I just do the square root of x around the y-axis, I'll get the volume of the funnel, okay. But I want whatever's outside. So it looks like just from our common sense and geometry, if I do the volume of a cylinder and then subtract the volume of the funnel, I'll get what I need. Do you see that? Now, of course, I can do the volume of a cylinder, just using the volume of the cylinder formula. But I want to get to a different formula here. So if I just do the volume of a cylinder using this technique that we just talked about, so what is the function that we're going to be rotating around the y-axis to get the volume of a cylinder? Yeah, x equals 4. So since we're doing the dy thing now, so this is just 4. So the formula is pi integrate 4 squared dy. What are the limits of integration? On the y. Yeah, from 0 to 2. So whatever this comes out to be, what is this? So it's 16 pi y from 0 to 2, right? And so 32 pi. This is just the cylinder. Now the volume of the funnel, again, we'll integrate from 0 to 2. What function are we going to be integrating? What? What is this function? If, well, the square root of x, that's y is a function of x. But when you look that way, you want to look at x as a function of y. Yeah. So, but you need to solve for x, right? X equals y squared. So that's what we're going to be rotating around the y-axis. So it's y squared squared. Is that okay? So this is y to the power 5. We integrate that. So it's y to the 5th. Sorry, y to the power 4. So it's y to the 5th over 5 from 0 to 2. Right? I'll resolve it already. So what do we end up with? 32 pi over 5. Is that right? Yeah, that's right. So this is the volume of the cylinder, 32 pi. Volume of that inside thing is 32 pi over 5. So what is the volume of what we're actually looking for? So what do we need to do to find that volume? Yeah, we need to do some, we need to subtract. So you'll go volume of a cylinder minus the volume of a funnel. So this is 32 pi minus 32 pi over 5. So what does that comes down to be? 128 pi over 5. Is that all right? Is that okay how we got that? Yeah. From 0 to 4, and then multiply by 2 pi. Well, I mean, it's not just... Well, you have to be more careful on that one. I mean, if you take that area and you want to just I mean, you have to be more careful when you do that. So when you have a shape and so it's the cross section state. I mean, it will get a little more technical. I mean, we'll deal with that later. Not yet. But anyways, what I'm trying to get at, this is silly to compute those two things separately. But if you understand that this is the difference of these two integrals, one was from 0 to 2 4 squared dy pi, and the other one was from 0 to 2 y squared dy pi, like that. I mean, if I do a little bit of manipulation, I will end up with pi times the integral from 0 to 2, and what I have on the inside is 4 squared minus y squared dy. Right? I mean, this is another way to look at this problem if I play with the integral. So actually, this is kind of the formula for computing the rotations that are bounded by two curves. You'll just take the outer curve squared minus the lower curve squared, and then just plug it in. Because this is kind of counterintuitive, because it feels like you should be dealing just with the area between two curves squared. But that's not the case, just by looking at this example. So in general, if you want to do something like this, revolution by two curves, we're going to look at this setup. So this is the r of x squared minus r of x squared, where the big R is the outside function, the bigger one. And the little r is the inner function, the smaller one. Okay? So it's not the difference square, but the square of differences. This is the big thing, because it's really easy to get confused on that one. And this is kind of from what we saw here. We might come back to this problem with it today. We'll do it differently. But, hey, for now, this is what you get. Any questions on this? Well, yeah, because with this technique, with the technique of what we call the disks, if you rotate around the y-axis, you will end up with a dy integral, because these are your slices. I mean, if we go back to the original thing, right? So you're looking that way, you have a dy integral, so it means all your functions have to be in terms of y.
The way it was, when you didn't do that, you would have swept it this way.
Right, I would sweep it this way.
And then you would have got
Community difference. There is another technique. You can keep the things the way they are, and this is what Owen was bringing up last class. You slice it differently, and I'll talk about it later. That's in 7.3. So this is what we call the cylindrical shells, like peeling a roll of paper towel. So you can do that way. So you'll keep the functions the same. So we'll see again, just like with the area, sometimes it's hard to get those functions. Again, dy integral works better than dx integral, so you can have different techniques of doing that as well. You'll get the same shape, but your different evaluation. But you kind of have to account, again, I'm jumping ahead, but if you make those slices and you rotate this way, so you literally get like a hollow cylinder, right? So there are a few things that are at place. Is this, the dx, and the height, but also the actual x value, how far away you're from the origin, to account for the radius of rotation. So the 2 pi comes in, x would be the radius, and then you also need to have a circumference that's from, 2 pi r, so 2 pi radius times the height and times the width will give you the volume of that shell. But we'll do that in 7.3. We might get to this today. But this way you can keep the functions the way they are. All right. Let's do this problem. Region bounded by y equals x squared plus 2 and y equals 10 minus x squared. And rotate around the x-axis. So x squared plus 2 is something like this, and 10 minus x squared is something like that. And rotating around the x. Okay? So we can actually start using the formula that we just discovered, is whenever the outer function, which is what? 10 minus x squared squared minus the lower function, which is x squared plus 2 squared, pi. And then the only thing is finding the limits. Yeah, you can just do 2 and make this one a 0. You can do that because it's...
So, because 10 minus y squared is on the top.
Yeah. So it's the bigger one minus the smaller one. Okay, and this is just you visually judge that. If you have a graph, sometimes it's hard to graph, you just calculate it or whatever. So what is the upper limit? 2, maybe? Does 2 work? Well, I'm sure we can. Just you were being facetious. Is that what? Oh, okay. There's a little sarcasm there. Okay. So you set the 2 equal to each other. You solve for x, right? You x squared plus 2 equals 10 minus x squared. So that's 2x equals 2x squared equals 8. X squared equals 4. X is plus or minus 2. So it's from -2 to 2 if you don't double it, or from 0 to 2 and double it. So we can do that. Okay? So you definitely, if you see the symmetry, use it, because, half of the integral is easy. Let's do this one. So what do you want to do next? Square those terms, so get all cute with it. Because this is a difference of squares, right? Do you agree with that? Square is square and a minus? Because I can get the result a lot faster if I use a difference of squares formula and just go a plus b, a minus b. See what I'm doing? Difference of squares, so this is a cancel, right? So that becomes 12. What's going on in here? 8 minus 2x squared. this right? Yeah. So the rest is what? The rest is simple. 24 pi, so the integral of that is 8x minus 2 thirds x cubed from 0 to 2. So now 0 gives you 0, 24 pi, 16 minus 16 thirds. Is that right if you plug in 2 in there? So whatever that is, it's 24 pi times 16 minus 16 thirds is 32 thirds. Is that right? 32? Yeah. 3 goes into 24 8 times. 256? Yes. 256 times. Yep. So here we didn't have to mess with the, what's the, like we were doing in the previous problem, figure out the big volume, figure out the small volume, subtract them. We just went ahead, just plugged it all into the formula. Whatever the bigger squared minus the smaller squared, the rest stays the same. Is that okay? Any questions on this? Okay. Well, let's do this. Let's rotate around different axes. So region bounded by y equals 2x squared, y equals 0, x equals 2, and rotate around y equals 8. So I want to do actually a very careful sketch here to see what we're doing. So 2x squared, something like that, x equals 2. Then when do they meet? 8, right? So that's almost fortunate. 2, 8. So this is the region bounded by 2x squared, y equals 0, x equals 2. Okay? Now the axis of rotation is y equals 8. So we're actually rotating around this line. So it will go up like that. We'll end up with this type of shape. This is the rotation. Okay? So again, we can just stick to this same idea, whatever the outer radius squared minus the inner radius squared, right? This was what we were doing before, right? This is always the outer function, which gives me the outer radius of the rotation, minus the inner function, which gives me the smaller radius of rotation. You subtract the two. Well, if you think about this, what is the outer radius of rotation here? What is going to be the size of that radius? right? The outer radius is 8. So I can go, okay, so this is 8 squared minus the inner radius, which is this. Well, yeah, eventually. Well, I can leave it the way it is. This because I'm rotating still. It's still kind of a right. It's 8 minus 2x squared. Right. This is how you find this distance. So this inner radius is 8 minus 2x squared, but then still squared. Right. Dx pi from 0 to 2. Did that make sense? This is a little okay. Because do you agree that this is my inner radius as I'm doing the rotation? This is what I want to take away, right? Well, what is the value of those rate lines at any point? Well, it's the difference between 8 and whatever this function is, right? So this is 8 minus the value of the function. So this is 8 minus 2x squared. Okay? There is another way of thinking about this problem. And whichever works, let me do this on the side here. So this was the thing that I was rotating, right? And this was that line 8, okay? So when I rotate it, I get that thing, right? Well, let me ask you this question. If I pretend, by closing my eyes very tightly, that this is no longer the line 8, but this is my x-axis, what is the equation of this? Because this will be equivalent to rotating this region around the x-axis. I'll get the same volume. Well, then this line right here is y equals 8, right? Well, what is this graph? Now it's that same upside down parabola, which is negative 2x squared, shifted 8 units upwards. So this is 8 minus 2x squared. So again, you can do the same thing. The outer radius, 8 squared, minus the smaller function, which is that squared. That's another way to just kind of pretend that the axis of rotation is in fact your x-axis, then just translate all the functions with respect to that, and then, did that make sense? Well, they both work. Again, if you just stick to the idea that it's always the outer radius minus, that's always the outer radius minus the inner radius, and then do the math, and it'll work. Is that okay? Let's do the math. What is it going to come out to be? From 0 to 2, so it's 64. 64s will cancel. So 64 minus 64, what is this? 1632 plus 32x squared, and then minus 4x to the 4th dx. Right? So now it's a simple integral. Whatever that is. Anyone who did that one already? I got 896/15 pi. Could be wrong. See if you get that. Did that work? Anyone's doing the math? Okay. So anyways. So any questions on this? So this is how you can do different axes of rotation. Just either stick to the rule of outer radius minus the inner radius, or you can always do that translation and rewrite your functions. You'll get the same thing. Okay? I want to do a fun problem now. I want us to find the volume of this shape. Of this shape. So it's kind of a topless pyramid. What do we call this thing? Yeah. So it's a square base. Okay? No top. If I throw some dimensions on it, let's call this side B, this side A, and the height is H. Okay? So if I slice this frustum, at any point parallel to the base, no matter where I slice it, what shape do I get? Well, no, I'm slicing it that way. I'm always going to get a square, right? No matter where I slice, I'm going to get some kind of a square, the cross section. So there is a way to find volumes of these types of shapes where the cross section stays consistent. Because really all I have to do is to figure out the volume of one of those little cross sections, right? And then just add them up. You know that? Because I can find the volume of that little, going to assume, little rectangular box or whatever, right? And then it's going to add them up. So there's going to be some, there's going to be some mathematical issues with that. But this is the idea. If I can find the volume and I can write it as a function of, how wide those things are at any given point, and stack them all together and add them together, I'll get the volume. Are you ready for this? This is going to get dirty because it's A, B, and H. It's always fun. If I put 5, 2, and 7, then it's easy, but it's A, B, and H. Okay? So first, let's do this. Just for the sake of making the math simple, we're going to put this thing on our axis in this fashion. So it's kind of centered like that. Is that close enough? So this is H. Then this point right here is what? If the entire base is B, I'm trying to center it around the origin. Well, not B, but half of B, right? Because I'm trying to do it in the middle, so it's half of B, 0. This point would be negative half of B, 0, right? Now, how about this point right here? Half of A, well, not 0, but H, right? And here you're going to have negative half of A and H. Okay? So it looks like this is the plan. I'm going to make my slices this way. Okay? So if I cut this piece, I'll get a little, a square base. This thing. So the height of each of those boxes, what? Delta y, that's right. It will turn into dy eventually. Okay? Well, the volume of this thing will be the side squared times delta y, whatever the s is. Okay? So what is s? Well, This will make it s over 2. That will make that negative s over 2. But we can avoid all those extra over 2s. We'll just call it, this whole, if I just call this point x, then the whole side will be 2x. You agree with that? It'll be easier if I just label it like that. 2x here and a 2x there. Is that okay? Okay, so basically all I have to do now is to express x in terms of all the rest of that mumbo jumbo. Right? You with me so far? Well, can we do that? Can we express x in terms of the rest of this junk? I mean, it's a straight line, right? I have 2 points on that line. I can find the equation of that line. And if I have the equation of that line, I can solve for x and get x equals whatever. Right? Is that okay? It'll be x in terms of y, and then we'll be integrating with respect to y. So that's all good. So we need to, find equation of the line given 2 points. What do you need to do? Are you with me, Gregory? Given 2 points, how do you find equation of the line? Yeah, equation of the line. You need to find the slope. Change in y over change in x. So let's do that. So what is this? Here are the 2 points. So you want to go h minus 0, then it's over a half minus, like that? Yeah, so you can say it's 2h over a minus b, right? So that's the slope. Are we okay with that? Well, it's the same logic as with the rotation, right? Because with the rotation, we're just adding a bunch of stuff. We're not rotating anything, but we're taking the same idea that the cross-section stays consistent no matter where I cut it. Okay, I mean, if this thing was twisted or there's some other issues that will get, but this thing stays pretty consistent, right? So every slice is that. So I'm just trying to figure out the volume of that. I'm just going to add all of them. The integral will come up. I mean, it's similar to the logic behind rotation. It's not quite rotation. The pi will not show up here because we're not doing anything circular or anything like that. But anyways, good? Slope. So then what is the equation? Y minus y1 equals m, x minus x1. You're probably easier to use the point b half 0, right? Because it has 0 for y. So then it's just y equals the slope, which is 2h over a minus b times x minus b over 2. Is that okay? So that's the equation of that line. So I can solve for x. So if I solve for x, I mean, I can just flip the slope to the other side. So this is a minus b over 2h times y equals x minus b over 2. So solve for x. X equals a minus b over 2h y plus b over 2. Right? Well, so this is just x. So what is the length of this whole side? 2x, right? So therefore, 2x would equal to just a minus b over h y plus b. Right? So therefore, the volume of each of those rectangular boxes will come out to be a minus b over hy plus b squared times delta y. Right? That's how we drew it over there, 2x by 2x times delta y. So something like that. Let me see, that's right. Um, yeah. So far? Now what are we going to do with that? This is the volume of just one slice. I want to do the whole thing. Well, yeah, do the Riemann sum, take the limit, turn into integral. I'm not going to do those intermediate steps, but it'll come out to be the integral of that, a minus b over hy plus b squared dy. And what are the limits of integration? We're doing the y integral, 0 to h. All right, so this is the big step. So we got this part. Now we just need to compute that integral. This is h.
So that a minus b over h is a constant one of the y.
Mhm.
Like that, so it'd be y squared over 3 plus 3y. But a minus b over h times y squared over 2.
Say it again.
That's not right.
I don't know. I lost you there for a second.
You can integrate. Oh, I guess square off crap first.
You can no, you're right by saying that you can just integrate by kind of u-subbing this because this is just y. So you'll go all this junk cubed over 3, but then times the reciprocal of what's in front of y. I mean, you can do it that way. You can say the integral would be a minus b over h y plus b cubed over h is here and then 3 a minus b. You can do it like that, or you can square all crap, do it term by term.
So it's just easy to do.
I actually don't know yet. We should end up with the same result. We might have to cube that mess. Maybe we should have squared first and then integrated. But anyways, let's see where it takes us. So plug in h. So we get h times a minus b over h times h plus b. Oh, good things happening already. Over 3 times a minus b minus, well, when you plug in 0, you just get h times b cubed. Oh, yes, this thing cubed. Is that what you're saying? Yeah. Over 3 times a minus b. Right? So what are the good things I was kind of talking about? Yeah, h's cancel. So then you end up with a minus b plus b. So minus b plus b cancel. So we're ending up with h a cubed minus hb cubed over 3a minus b. I can do some more creative factoring, right? Take h out, use the difference of cubes formula. What? Oh yeah, this is the difference of cubes formula. A minus b times what we call a degenerate quadratic, missing a deuce in the middle. So it doesn't factor any further. Oh yeah, you can factor all of them. So it's really h over 3 times a squared plus ab plus b squared. Looks like that's, what was that? So, is that what I got before? No, that's not what I got before, but I don't know, maybe this still works. Well, yeah, I got, see, I did it differently before. What was that? Somebody said something about, what? Yeah, no sig fix. Um, well, let's do some special cases just to test this formula. Let's say A equals B. Let's look at the first term where A equals B. What do you get really? What kind of shape is that? Well, it's not necessarily Q, but it's a it's yeah. So it's a square base box, so parallelepiped with a square. It's a well, anyway. So we know the volume of that should be B squared A, right? If that's the case, well, let's see if that works. B squared H, yes, B squared H. So if A equals B, so let's try that. If we plug in B squared plus BB plus B squared, so yes, this is H over 3 times 3B squared, so B squared H. So that kind of worked, right? Another fun case, if A equals 0. If A equals 0, what do you get? You get a pyramid, right? So if we plug in 0 for A, we'll actually get a formula volume for a pyramid, which is actually not easy to derive, but now, hey, look at that. V equals H thirds, well, B squared, right? That's all there is left. So, hey, HB squared over 3, volume of a pyramid, of a square base. Is that true? Who has those formulas? Flip to those formulas on the front of your book.
Is it true for any regular polygon? Like not B squared, but the area?
Yeah, it's a third area times the height. Is that true? The volume of a pyramid is not in there?
Just line of code.
Yes, it's 1/3 pi squared h. Yeah. There's no pyramid. Oh, good then. We even did more. Is there a class coming in? There's a bunch of people here. Oh, you're giving a tour.
He's a math whiz, though.
They're giving a tour. I thought they were. But isn't that cute that we can do that? I mean, if the cross section stayed the same, just same kind of process, pain, but we got it, right? That's interesting.
Can you also derive that by taking the greater pyramid and subtracting the smaller pyramid?
Yeah, you can do that, right? I mean, it's just, I mean, your heights are, I mean, you can derive that, right? So you take two pyramids, one with a, yeah, the big pyramid with a height h and the small pyramid with a height h minus. Well, wait a second. Well, you have to, yeah, you have to relabel things a little bit, but you can do that. Cool. All right, so let's try this problem. Y equals, so going back to rotating things a little bit, and y equals 0, so region bounded by that, rotate around the y-axis. So this is a cubic, so cubics are kind of fun. I mean, if I try to find the intercept, so pull x squared out, and then it's 2 minus x. right? So the graph of this thing, this is 2, this is 0. The graph of this thing is something like that. And so we're bounding it by y equals 0. So this is the shape that we're looking at. But then the problem is that we're rotating it around the y-axis. Well, that's what we're driving at. Because do you agree that if I rotate this around the x-axis, no problems whatsoever, right? You're staying consistent underneath the pretty function that's defined. You just do whatever we've been doing so far. But I'm rotating it around the y-axis, right? So using the technique that we just did, where these are my slices, will I be able to do it like that even? I mean, I'll have to figure out this point and kind of solve for those little chunks. I don't even think that's, well, yeah, I can find that point, but solving for the x in terms of y, it's going to be, I mean, it's doable, it's a cubic, we can solve cubics, but it's a mess, okay? So again, the question is, can we do it this way? And you guys already heard us mentioning this technique a few times. Well, this is called the shell method. The washer method is the same as the disk method, because these are the slices of like washers. It's a disk with a hole in the middle, same thing. But here's the idea. So for those of you who've never done that before, because think about this, I'm rotating this, each of those slices also being rotated around the y-axis. So what I'm ending up with kind of a can, right? If I just rotate this piece, this one little rectangle, around the y-axis, I'll end up with a little can, right? That's what Owen was saying about roll of paper towel and just whatever you do with it, unrolling it, okay? Yeah. Yeah, because we eventually that's what we're going to try to do. We're going to try to find one of those cans at throughout this X region. Okay. Now, if I take one of those things and just let's talk about this. So here's my little X sub I. That's why I'm doing my slice. Okay. Well, I need to know the volume of this shape. So few things. What is the radius of this thing on the bottom? What is the radius of the base? Yeah, whatever the x is, right? Whatever I took that slice, that's what the radius is. What is the height of this thing? Yeah, this is f of x sub I, right? It's still in terms of x. F of x sub I. And what is the thickness of these walls? Right, delta x. Do you agree with that? Now, to find the volume of this shape, the traditional way we do that, we cut it and we flatten it out. That's a rectangular box again, right? If I cut it up and I flatten it out, it's like that. So the thickness is delta x. This side is the function f of x sub I, right? Well, what about this side? 2 pi x sub I. This is the circumference of the base, which is 2 pi r, and r is x sub I, so it's 2 pi x sub I. So the volume of this thing is 2 pi x sub I times f of x sub I times delta x. This is the volume of each of those shells. Okay? So now we're going to add them up as n goes from, whatever as I goes from 1 to n, 2 pi x of I. And we'll take the limit, so we'll turn into an integral. So that will become, I can pull 2 pi out, and then it's an integral from a to b, x, f of x, dx.
How will you take up the part of the vector inside outside?
Yeah, but again, remember, so this is why I'm just calling it x sub I. Just it's a point somewhere on that region. Again, remember, this region is going to shrink infinitesimally small, so that wouldn't matter. You know what I mean? So, is that okay? I mean, this is what you assume with all the integrals, right? You do the left-hand point, the right-hand point, but who cares? It's all going to be the same anyways when you make it small enough. Is the rest okay? So if I just operate with this formula, it will come out really nice for this problem. Because now, in order to find the volume, all I have to do is to go 2 pi, and this is a dx integral now. This is a nice thing. Rotating around the y gives me a dx integral. Rotating around the x will give me a dy integral. So now in the future, when given a problem, you're just going to look at the function and say, well, which way is this function? Well, how does it act in each way? If it's awful to do a dy integral, then you can always do a dx integral with a different method. Okay. So what's going on? X, the function was 2x squared minus x cubed dx, and integrating from 0 to 2, so that'll give me the volume of that shape. I got 16 pi over 5. Okay? I mean, you can compute that, whatever, it's not hard. But one thing with method of cylindrical shells, by the way, this is 7.3 already. The rotation around the horizontal axis, or we'll just call it x-axis, you'll end up with a dy integral. You're going to have volume equals an integral from a to b, y, f of y dy with a 2 pi somewhere. So that's when you rotate around the x-axis. And around the y-axis, you'll get volume equals an integral from c to d, because it doesn't have to be the same as ab, 2 pi x f of x dx. Okay? So I want to do this one example. We're going to do it a few different ways. So let's say here's the region bounded by y equals x squared. And let's do rotate around the x-axis. And I'll do it both ways. Okay? We'll do the disk method or the shell method. So we'll do both. we're rotating around the x. Okay? So first, let's use the disk method. Or washers. Because again, you get disk with a hole in the middle or whatever. But so remember how we did that one. So we're rotating around the x. So this is the way we view our slices. So it's the bigger radius squared minus the lower radius squared. Right? So what will that give me? What is my bigger radius? X, so it's x squared minus the lower radius squared, so x squared squared dx from 0 to 1. So that's using the 7.2 technique. So if we do the math, so it's pi and then it's x cubed over 3 minus, so this is x to the 4, so it's x to the 5th over 5 from 0 to 1. So it's pi times 1/3 minus 1/5. And what's 1/3 minus 1/5? 2/15. So it's 2 pi over 15. Yep. Is that okay? So that's using the disks. So questions on that? This is a very nice problem, by the way. There's nothing funky going on. We're good? Okay. Well, let's do the shells. So this is section 7.3. So first of all, what kind of an integral are we going to end up with? Dx or dy? Dy. So it's going to be dy integral. Y will still range from 0 to 1. Do you agree with that? So y goes from 0 to 1. The radius is y. The only thing is we need to find the function. So what is the height of each of those shells at any given point? We have to be very careful here. We'll look at it that way. What is the height of each one of those shells? Yeah, it's whatever this line is, so it's square root of y minus whatever that line is. Right? Do you see that? So it's square root of y minus y. You want me to draw the rotation feature?
No, I just didn't know if you have like you're always cutting and pasting stuff.
Oh, the thing? Oh, maybe it does. I haven't gotten that deep.
That would be cool.
That would be cool. Yeah, there was this. I was in the market for some chalk a couple of years ago, and I came across the 3D chalk that comes with the glasses. I was like, ooh. You know, in that room 117, you got a chalkboard, so you can actually get it all and get the old glasses. But we haven't, it's ridiculous. But anyways, so let's try that. So it's 2 pi from 0 to 1. So distribute that. So what do we get? Y to the power 3/2. Is that right? Minus y squared dy. Integrate that. 2 pi, and then we have y to the power 5/2 times 2 over 5 minus y cubed over 3 from 0 to 1. Is that okay? So you plug in 1, you get 2 pi times 2/5 minus 1/3, which is 2 pi times 1/15, which is 2 pi over 15. So we did get the same thing, right? Yeah, here it is. How's that? Good? You need a cigarette? Oh, is that what's going on? Well, I'm